Hi, welcome back. I'm George Trimble, and this will be our fourth installment on celestial navigation. This time, as I promised last time, this time I will show another approach to solving the spherical triangle that is so important in obtaining what's called the intercept distance and the zenith, the two values needed to put yourself on a map and find longitude and latitude at sea. Now, we used the method of the spherical law of cosines, and it's mostly what is taught is the spherical law of cosines, and I showed you how to derive that in the last video. But I promised you I'd show you another approach. In this approach, we're going to use the 10 spherical right triangle relationships. We'll derive them. They allow us to learn something about a missing side or angle of a spherical triangle if we know two or more of the other values of the triangle. But it only works on right triangles, and so we'll end up having to divide the spherical triangle into two triangles by cutting it in half, and then we will apply the right triangle relationships to see if we can't solve it for another way, or solve for the values we need in another way. And so this is really optional stuff. It's for those who really want to understand how the mathematics works behind spherical trigonometry. You really don't need to understand this in order to use the typical spherical law of cosines to solve, but this is really for the mathematical masochist. So, welcome if you're one of those. Join me now, and I'll show you yet another approach. This is the first approach that I came up with before I really understood the law of cosines, because at the time I couldn't derive it. I couldn't figure out how to make it work, and I just hate to use equations that I don't understand. So here we go. This is going to be us at the end, but jump right in now. Now here is our celestial or navigational triangle. It's comprised of cut sections through the sphere, planes that intersect not only 2 points on the surface of the sphere, say, for example, the North Pole and the location of the boat here at this corner, but it has to intersect the center of the sphere as well in order to be considered a great circle. Not a small circle, not a secant slice. We're talking about a great circle, which by definition has to go through the center of the sphere. And when we intersect three such planes, three such great circle planes, or cut sections through a sphere, they create a triangle on the surface. And the sides of this triangle, at least in terms of celestial navigation, are the colatitude, or 90 minus the latitude, understanding that somewhere down here is the equator, and that the distance up from the equator to this point is the latitude. And the distance up from the equator to this point is the celestial equivalent of latitude, called the declination. And so this value here would be 90 minus the declination, or the co-declination, and this is the co-altitude, which in nautical miles is the same as the minutes of, or I should say arc minutes of separation at the center of the Earth between the boat and the celestial body's geographic position shown here. We'll say, for example, the sun. So there's our celestial or navigational triangle. Pardon me. For the time being, just for the time being, and this would not generally be the case, we're going to assume this is a very atypical celestial or navigational triangle in that it's a right triangle. In fact, let's just dispense with briefly the idea that it has anything to do with celestial navigation, and we're going to call it a geometric object, a triangle on the surface of the sphere that happens to have one right angle. Now, we're going to look at it in an oblique view like this, and respecting the idea that these corners, the edges of the triangle, are connected via a radius to the center of the sphere, and remembering that this angle here is the right angle, we are going to remove this wedge, this cut section, from the sphere and bring it out to look at separately like this. And just for sake of simplicity, we're going to say that the radius of this is 1 unit, and we could say it's 1 radius of the Earth. All right. Typically, we label angles with capital letters, so I've got A, B, and C, and O for the origin or the center of the Earth. Now, I'm going to move me over here. I've put in the named sides, co-declination, co-latitude, and co-altitude, but in spherical trigonometry in general, we name the sides as the little value, like little c, opposite the angle. Here's the angle B, big B, so this is little b. Here's the angle big A, little a. Enough said. They're the angles, again, shown at the center of the Earth. And we recognize that, at least in celestial navigation, we understand that the distance between A and B in nautical miles is the same value as the arc minutes of separation of this angle at the center of the Earth. That is the principal driving understanding behind celestial navigation. So let's see what we can do with this triangle, this celestial triangle. We're going to create AE perpendicular to OB. So we're going to create AE perpendicular to OB. So that's a line like this, and it's perpendicular, so we understand that OEA is a right angle and AEB is a right angle. All right, and we're going to create ED perpendicular to OB, such that it intersects OC. Now, that means it's perpendicular here, so the angle DEB is a right angle, and the angle DEO is a right angle. That's what this second statement says. And the next step in our construction is to create AD perpendicular to OC. Here's OC, and we're going to create AD, and it's understood to be perpendicular to OC. And that means that this angle here is right, that's ADO, and ADC is a right angle. Okay? Now we're going to imagine a plane tangent to the sphere at B, like a glass plate, touching the globe at B, and therefore it has to be perpendicular to OB, this line. And that's what this is saying. It's tangent at B, and therefore it's perpendicular to OB. Now, you don't see the plane yet. I'll show you here in a minute. But in fact, let's see here. And before we move any further, I want to show you that just because this line, AD, is perpendicular to OC, it was constructed that way. If you look at a top view down looking through A, you can see that this line ED, while perpendicular to OB, that's this line ED, that line is not perpendicular to OC, okay, at D. So that's the top view looking down. But AD is perpendicular to OC, and AD is sticking straight up through this point right out to your nose. And it's perpendicular. All right, so that's one thing I wanted to point out. Angle ABC is equal to angle AED. Okay? Do you see how this angle here, AED, because AE lies in the same plane as the plane that contains AOB, and ED lies in the same plane as the plane that contains COB. These angles are, in part because they're perpendicular, ED is perpendicular to OB, so that AED is perpendicular to ABC. All right. Now I'm going to show you the plane. And you can see that a plane kissing the sphere at point B, which is here, can be a receiving surface. Imagine this. It can be a receiving surface for a shadow cast by a light at the center of the Earth. The light is cast up through B, and the light casts shadows of these lines through this glass sphere. I made it glass on you, sorry. And so these lines, AB and BC, are cast onto the plane as straight lines. And they have the same angle. ABC is the same angle here between AB and BC is the same angle as between these two shadows cast on the surface of the plane. And you can see that AED is also of the same angle. All right. That's an important finding, and we're going to come back to that later. Here's our drawing. Now, I see we got a little random red square on the screen. Hopefully that's going to make sense here in a minute. What we're going to see here shortly is that we can do some geometry with this. Now, do you see that we've got this triangle here, AOE, with its angle enclosed C, and we've got this back triangle here, AOD, right here, and its enclosed angle B here. And these triangles are made because we constructed this strange triangle in the middle here. And why we did it is important. It helps us make some progress here shortly. And we've also created this little triangle on the bottom here. Now we're going to try to work from the angles at the center here, C, B, and A, and these sides, and somehow discover some relationship between the angles and sides of the spherical triangle at the surface. And let's see if we can do that. All right. So, let's work with this first triangle here, okay? And I want you to see that this angle C and this right angle allow us, and it's right angle because it was constructed that way, remember that. It allows us to make some deductions about the sides. For example, we can discover AE and understand that AE would be the sine of angle C, right? Understanding the radius is 1. So the sine of C is the upright side, AE, over the hypotenuse, which here is taken to be 1, the radius of the Earth, 1 Earth radius. And so AE over 1 is just AE. And so this value here, AE, is the sine of C. And we can discover the cosine of C in similar fashion. It's OE over 1 or just OE. So OE, this value of this, the length of this side is the cosine of C. So I put them in there. There's the sine of C. Do you see it here? And we discovered that and we got this triangle from this bigger drawing. So let's transition those values up to the main drawing as we find them. What we're trying to do is discover all the sides of this interior red triangle. Now, I told you about the cosine of C down here, so we'll put that in. We've discovered that length OE is the cosine of C. Now let's turn our attention to angle B here in this triangle. This is the far side of the pyramid, so to speak. And the sine of this, understanding that although this is a strange little shape down here, this is distorted due to perspective. Remember, we constructed this as a right angle, and so this red box here reminds us that it is in fact a right angle. ODA is right, and therefore we are justified in saying that the sine of angle B is AD over 1, or just AD. So the sine of B is AD. Here it is right here. And so we can put that in, and that represents that side. And the cosine of B is OD over 1, like this. And that's this line from here to here. The length of that is cosine B. All right. And that's interesting because it's going to allow us to discover this length in here. And I'm going to show you here. We're going to find the tangent of A. Okay, that's A right here. We're going to find the tangent of A. And that's the sine over the cosine, or this upright over the base, or the opposite over the base. So that's ED over OE. ED over OE right here. But we've already discovered that OE here is also known as the cosine of C from this previous discovery. So I'm replacing OE with cosine of C here, and that allows me to isolate side ED by multiplying both sides by cosine C, and I end up with this value. So length ED is given by the tangent A cosine C, and I've expressed that here, tangent A cosine C, and that's up here as well. Okay. Now, I recognize that there's another way for me to express the length ED, okay? And I can take the sine of A. The sine is the opposite, ED, over the hypotenuse, OD. But we've discovered OD already. It's the cosine of B. So I've got ED over OD, ED over cosine B here. And I can isolate ED by multiplying both sides by cosine B. And so I have sine A cosine B is equal to ED. So I've got two values for ED. I've got tangent A cosine C or sine A cosine B. Both of those can be used, and we'll see shortly how to use them. All right. Seems like a lot of work. All right. So now I'm taking just the part of the previous drawing that interests me. It's the spherical triangle and the planar triangle. And I show you here that I've discovered a value for this side, a value for this side, and two values for this side, depending on what I want to do. No. Oops, sorry. And recalling that angle ABC, as I took great pains 2 slides ago to show you, is the same as AED. This angle equals this angle. Now they have the limbs have different characteristics, but one is a projection of the other. Pardon me. And to simplify this, we're just going to call this angle B, and we're going to call this angle E. And so I'm just going to say that B equals E, same thing. Okay. Now, we have sine B, okay, is equal to, the sine of angle B is equal to the sine of angle E. Whatever it is, we don't know what it is yet. We know that if B equals E, then the sine of B must also equal the sine of E. And we know the sine of E. The sine of angle E, being that this is a right angle back here, is simply the opposite side over the hypotenuse, or the y value over the radius value of the triangle in standard position. And so we got sine B over sine C. And we get that the cosine of B must be equal to the cosine of E, since B and E are the same, it says right here. And so to find the cosine of E, we take the base over the opposite side, or rather the hypotenuse. And since the hypotenuse here is couched in terms of C, we choose this formula, tangent A cosine C, because it too is couched in terms of C. And so tangent A cosine C divided by sine C is the base over the hypotenuse. Okay. And we can find the tangent of B. This is B. If it has a tangent, then it must be the same tangent as E, because angle B and E are exactly the same. They are the self-same value. So if I can find a tangent of E, then I have discovered a tangent for B as well. And so the tangent of E is the sine, or I should say, it is the sine over the cosine, but it's also the upright or opposite side here divided by the base. And in this case, since the sine is couched in terms of B, I'm going to use this value, this here value for length ED, because it too has a B in it. So I'm going to say that sine B divided by sine A cosine B, and that's here. Now we'll simplify. I'm just saying that this equals that. And I'll do that for each of them. So those are the interesting findings we have. Now let's see if I can put me somewhere. Now we're going to derive 10 relationships. Here's 7 of them on the first page. And these are relationships that we need to think of, we need to have handy in order to solve spherical triangles. For example, by simple manipulation, if I want sine B by itself, I'll multiply both sides by sine C, and I come up with this equation, and that's known as equation number 1. What does it say, by the way? It relates the side B, the side B of a triangle, a spherical triangle, okay, to the angle B and another side, C. And so, unlike in planar trigonometry, where the relationships are just, say, for example, the tangent of an angle is the upright over the base, right? These look more complicated. Here we've got the sine of a side is equal to the sine of an angle times the sine of another side. And they're couched in terms of signs of things, not things themselves. And so with spherical trigonometry, the formulas that we're used to look funny. They look different. Now, taking this other, these are the three equations we derived on the previous slide. I'm just manipulating them with algebra to isolate or to simplify them. Now in this case, I'm recognizing that the cosine C over the sine C is nothing more than the cosine over the sine is the cotangent. It's simpler to call that the cotangent of C, and so that's what I've done here, and it's known as equation 2. Now, what I want to do is make this equation look like this one here, because that's number 3, and I'll show you that the tangent of B is also known as the sine of B over the cosine of B, and that's equal to the sine of little b over the sine of little a cosine of little b. Now, I isolate sine A. How do I do that? I multiply both sides by this whole thing, okay? And then I divide both sides by this whole thing. And then this thing over here that was up here, I put on the bottom. And so, or I'm sorry, this thing over here I put on the bottom so that it ends up here. By moving things around algebraically, I can isolate A. And so what I have is sine of A is equal to sine B cosine B over cosine B times cosine B over sine B. And you can read on the screen the big and the little ones. And then recognizing the sine over the cosine is a tangent and the cosine over the sine is the cotangent, we've come to equation 3. I probably should have broken this down into a few extra steps, but I'm hoping you see that it's just simple algebraic manipulation. Now, we can find another value, number 4, by remembering that the length of the line ED has two values, both tangent A cosine C or sine A cosine B from the previous slide. And so essentially what I can do is equate them. And I do. I equate this equals this, and by a little algebraic manipulation dividing both sides by tangent A, I come up with this equation. Cosine C equals sine A cosine B over tangent A. And then I recognize that the sine over the cosine, and then tangent A is the cosine Oh, yeah, okay. I'm sorry. I sometimes lose track myself. Notice here's a division, okay? And here, sine over cosine, this is a division. The tangent is the sine over the cosine. But if we divide, it's like multiplying by the reciprocal. So I multiply by the cosine over the sine. That's a tricky little step, and I should have put an extra step in there to show it. But I'm changing division into multiplying by the reciprocal, recognizing that tangent A is sine over cosine, and so sine over cosine, and I'm flipping it to cosine over sine. And so what we have is cosine C equals, you see how sine cancels here? So we have cosine B times cosine A, and that's 4. All right. Now, from 1, now let's see, what does this say under here? All right. So now we've derived 4 equations just like that. And it's with the understanding that we selected A as the place through which to pass a plane containing this red triangle and create this figure. But we could have chosen B as the location to make the figure down this way and just turned this thing over on its side and done all the same reasoning, all the same steps. And what it would do is it would change 1. Essentially, it would change little b for A and big B for big A. And that's what I've done here. Sine little a equals sine big A sine C. You see, it's just looking at it from another perspective gives us 3 more equations just like these, 1, 2, and 3. Okay, and the only thing that's been done here is switching big A for big B and little b for little a. Okay, you can see that this is the same as this, making those replacements, and that represents us going through all the work of setting up this thing here, but taking this triangle through B, perpendicular to this line here. So using that approach, that perspective, we come up with 3 more equations like this, 5, 6, and 7. So from 7, and that was sine B equals tangent A cotangent A, we can isolate cotangent A and by dividing both sides by tangent A, and we get this. And from 3, sine A equals tangent B cotangent B, we can do some rearranging to isolate cotangent big B, and we get sine A over tangent B. And then if we multiply these two together, this by this, cotangent A times cotangent B, what we're multiplying is this by this, and we get this thing here. And recognizing that the tangent is the sine over the cosine, the tangent is the sine over the cosine, and basically we've got we've got this situation again where we're dividing by a fraction. We're dividing by a fraction, and it's like multiplying by the reciprocal. So if I change this division sign into a multiplication, then I have to flip these over. So now this becomes cosine on top and sine on bottom. And I do the same trick over here. I change this division into a multiplication, and then I turn this into a reciprocal, cosine over sine. See that? Now it allows me to cancel sine, and what I get is cosine A, cosine B is equivalent to this. Cotangent A times cotangent B, cotangent A times cotangent B equals this times this. Cosine A, cosine B. But from number 4 on the previous slide, we know that the cosine of C is equal to cosine A, cosine B. So I can substitute for this. I can just call that cosine C. And so now I have cosine C equals cotangent of big A times cotangent of big B, and that's our 8th, our next one. Now we only have 2 more to find, and then we've discovered all of the right triangle relationships that help us find missing angles or sides based on other sides or angles. Okay? And there they are. And using the exact same argument from 2, 5, and 4, I can develop this, which we call number 9. And using 6, 1, and 4, again, same thing. I can use that same logic as number 8 applied to the discovery of number 8. The same logic will get us 9 and 10. And there we've got our complete set of the right spherical triangle relationships. There they are, right there. Now, you might say, how am I supposed to remember those? You thought you were doing pretty good just to remember what the sine, cosine, and tangent were in plane trigonometry. Those 3 do most of the duty needed to solve triangle relationships and missing parts. But here we got to remember 10 relationships, and it seems more complicated. And so that brings us to how do we remember these? And I'm going to show you something called Napier's rules. And the rules for Napier go like this. We're going to draw a little, it's a memory aid. Now I'm going to cover that up. Napier's rules. All right. It's killing me. Hello, world. So here's our triangle, our spherical triangle. Understanding that this is a right spherical triangle at C, and C being special, angle C being special, we're going to leave it out of this diagram. we're going to draw a diagram like this, a circle, and we're going to divide it into 1, 2, 3, 4, 5 parts, okay? 5 pieces of pizza, 5. You can't forget that now. And let's count starting here. 1, 2, 3, 4, 5. Skip C, go right back to 1. Okay, and that's what this triangle does. So we've got A here and A here. The next thing skipping C is B, and then A, and then C, and then B, back to A. So we're just walking around this triangle, and we've put it into this nice little spherical pizza pie diagram, okay? And we recognize that were C to be included, it would have been fit between A and B, as you see over here. But we're leaving it out intentionally. And it's strange because the two values next to C, A and B, don't have a little line over them. The values opposite C, not touching C, do have a little line over them. And that little line is an indicator to us that we're using them in a special way. Big B line over it, little c line over it, and big A line over it. I'll call them B bar, C bar, and A bar. These are to be understood as the complements of the values. What is a complement? It's 90 minus the value. It's what's left over from a right angle when you take the original angle out. It's how much more do you have to go to get the whole right angle. So it's 90 minus the angle. Okay. So if angle B down here were, for example, 20 degrees, then B bar would be 90 minus 20, 70. So here I show you that B bar is 90 minus B. Now, as long as we understand that, we won't get confused. So we remember how to construct this, and for some reason, this sticks with people. C's left to the side, the two next to C, no bar. All the others have bars. Okay, so it seems like a lot. I told you this was going to be torture, but for those of us who like mathematics, this can be fun. Rule number 1. The sine of a middle part is equal to the product of the cosines of the opposite part. And look here, when we put that rule, I-I-O-O-O-O. Sine middle, cosine opposite, cosine opposite. So, for example, if we want to consider this a middle part, A, we would say the sine of this middle part is equal to the cosine of the product of the opposites. The cosine of this times the cosine of this. This is the opposite of the middle part. Okay. Rule number 2. The sine of a middle part is also equal to the product of the tangents of the adjacent parts. So look here, sine middle, tangent adjacent, tangent adjacent. Notice when you're using tangent, you're going to use adjacent because they both have an A in them. And when you're using cosine, you're going to use opposites because they both have an O in them. And that's why this is coded this way. So a sine of a middle part, say A, is equal to the product of the tangent of this adjacent and the tangent of this adjacent. You see why this is in the middle? It's between these two, or it's between those two. All right. So you can remember that as I equals O, or I equals A. All right. Now, so let's take, for example, the first scenario. Using the example that I started with, A, the sine of a middle part is equal to the product of the cosines of the opposites. Cosine of C bar times cosine of A bar. But we know that C bar is 90 minus C, and A bar is 90 minus A. Okay? And the complement identities, and we've in my previous lecture, you saw that the cosine of a complement value, like 90 minus something, is the same as the sine of the angle itself. So I can change this value, cosine of 90 minus c. The complement identities tell me I can change that into the sine of just c by itself. And the cosine of 90 minus a, well, that's just the same thing as the sine of a. So what I've done is changed sine a into sine c times sine capital A, and that's number 5 in our list. If we keep going and do all of the rules for all of the parts, we will recover 2 equations for each part, and that's a total of 10. So we can recover all of the identities. Now, I'm going to show you how we can think about the navigational triangle in a different way. The navigational triangle, of course, is not in general a right triangle. The right triangle is kind of a trivial solution. In general, the complexities of where the boat is and where the sun is mean that this triangle is going to be non-right. And so it's going to require either that we use the Spherical Law of Cosines, which we covered in our last lecture, or I'm going to show you today how we can think of this in a different way and use those trigonometric identities that Napier helps us remember to solve this triangle using another strategy. Now, I'm doing this just for fun. You don't have to use this, but this is how I first discovered how to solve the navigational triangle. We are going to cut this angle with we're going to drop a perpendicular to the colatitude. We're cutting this angle because we know nothing about it. I've never told you anything about what this angle is called. We know, for example, this is the azimuth or the zenith, depending on where it's located. This is the local hour angle. But we never gave this a name, and we've never tried to discover it, and we have no need for it. And so this is the angle we're going to destroy by cutting it in half, because we don't want to cut this in half, or, well, not really in half, in parts, 2 parts, neither of which part we know the value of. Will destroy information in doing so, and we don't want to destroy this angle by cutting it in some portion, and neither of which we know. We just know that we're going to cut this angle here, and we're going to declare that this line hits this line at a right angle, perpendicular. Okay, that allows us to pull aside 2 triangles. Now this top triangle, I pull aside, and I flip and turn it so it's in standard position with the right angle at the lower right. And I label it A, B, and C. In typical fashion, I'm allowed to. Those aren't the values that it had originally, right? But then you see, I've called the local hour angle A here. We'll never know what B is up here because that's been a cut. That was cut from an angle we didn't know in the first place. And I'm going to call this mysterious side here, I'm going to call it perpendicular little a because it's across from big A. And this side down here used to be part of the colatitude. That's here. Here, it's right here. It's part of the colatitude, but we've cut the colatitude in parts, and so we're just going to label the parts Y and Z, okay? And here I call it Y with sub B because it's opposite of big B. It helps us remember the relative positions of things because it's going to get complicated here soon. Now, with respect to this triangle here, I can say that the sine of angle A, the local hour angle, is sine A times sine C. I'm sorry. The sine of side A, that's here, is equal to the sine of the angle A, the local hour angle, times sine of little c, this side, okay? That comes from 5. And the reason I've relabeled these angles, A, B, and C, is so that we can use the right triangle relationships to solve this triangle for perp A, as you'll see. So substituting, sine A is sine of the perpendicular, and sine big A is sine of the local hour angle, and sine of C is sine of the codeclination. Do you see that? I know it seems complicated, and it is. And I can find the perpendicular, or isolate the value of this perpendicular length by taking the anti-sign of both sides. And here I do just that. Now, sine B, and this is equation 7, sine little b equals tangent little a cotangent big A. Now, that's the same as saying, well, b is this little thing here is y. Okay, that's this. And it's equal to the tangent of little a, that's here, the perpendicular, and the cotangent of this angle A, which is the local hour angle. Okay, I decided I wanted to find the value of y here, and in the previous equation I decided I want to find the value of the perpendicular. And you'll see that this is a step to solving this bottom triangle. If I know the perpendicular value of this triangle, then I automatically know the value of the perpendicular side on this triangle, this one right here. Okay? And if I know the length y, which we're going to discover right now, we take the anti-sign of both sides. If I know the value of y, then I know the value of z, because the colatitude minus y will give me z. Do you see that? So I'm moving from solving angles and sides, really sides on this top portion, and that helps me solve for things in the bottom portion. Sorry, I've got a bouncy mouse. It went backwards. Okay, that's where we ended up. Now, we're going to take this bottom triangle. We're going to flip it into standard position. I just flipped it. Okay, so, and then I label it in the same way I labeled the other one, typically B, A, and C, just like that. And there's the perpendicular. There it is here. It's the opposite to A. And here's the coaltitude. It's opposite of C, so I label it sub C. And here is Z. That's this value. Okay? And I label it sub B because it's opposite of B. And these little sub values help me know how to use the 10 right triangle relationships to help me find something about this. Now, Z, we know, has a value of the colatitude minus y, which we discovered right above here. Now, Z is the colatitude minus this, sine inverse the tangent of the perp times the cotangent of the local hour angle. So we've discovered the value of Z. And we've discovered it in terms of values we know. Latitude, the value of the perpendicular, which was discovered here. Okay. Now, the cosine, we're going to use number 4. Cosine C equals cosine B cosine A. And recognize that little c is the coaltitude, little b, that's Z, and cosine of the perp, that's little a right there, little a, there we go. All right, so this formula allows us to solve for the coaltitude by taking the anticosine of both sides. Now, filling in, the coaltitude then becomes the cosine inverse of the cosine of Z, but Z is right here. So I put all that, you see? cosine inverse of the cosine of z. The cosine of z is all that, so it's right there. Local hour angle and local hour angle. Okay, and we're gonna. it seems like torture, and we're gonna multiply it by the cosine of the perp. But the perp is right here. The perpendicular side is up here. So I've got the cosine of the sine inverse of the sine of the local hour triangle times the sine of the codeclination. There it is. And so if the coaltitude is that, then 90 minus the coaltitude is just the altitude. And the altitude is also known as hc. That's the computed height in sailorly parlance, remember. And so we take 90 minus this horrible equation up here, right here. 90 minus that is the altitude. And there you go. And that's what we're looking for in celestial navigation, right? We want to find the coaltitude, or I'm sorry, the HC, the altitude, the calculated altitude, for comparison against our observed altitude, the difference between them being the nautical miles between the assumed position and the ship's position. I'm just going to plug in my battery here. Now, sorry, not very professional, but this isn't what I do for a living. I'm not begging you for clicks and subscribes, so. Okay, so now we're going to use relationship number 6. The cosine of big A equals tangent little b cotangent little c. And let's see what that gets us. The cosine of big A is the cosine of the azimuth. Yes, that's what we need. We need to discover the azimuth. And that's why I chose number 6, because it has something to do with angle A, and it couches it in terms of B and C. B, we know, that's up here, and C, we know, that's the coaltitude, which we just discovered here. So the cosine of the azimuth times the tangent of Z, that's here, times the cotangent of the coaltitude. And we take the anticosine to isolate the azimuth, and so the anticosine of all of this in the previous side equation. And then when we fill in the tangent of z, well, z is all of this, and we've put in the cotangent of the coaltitude is all of this right here. This equation gets way out of control. So the azimuth is equal to all of that, okay? So now we've got this crazy equation for the azimuth. We got the crazy equation for the coaltitude, and you can see why, although this is perfectly valuable, it gives you the exact same answer as if you were to use the spherical law of cosines. The spherical law of cosines is so much easier. It's so much simpler. Now what just happened? Oh, that was it. So, I don't know if there'll be another one. I'll have to give it some thought. Usually at this point, I talk about what I'm going to tell you next time. And in my classes in person, I teach how to actually use a sextant. But I've noticed that there's probably 5 billion other people on the web that have taught that, and there's no need for me to recapitulate their efforts. At some point, I guess at some point we'll do how to reduce sites for non-solar bodies. So that's what's next for us. We'll talk about how to do stars, eventually lunar distance, shiver, and planets, and how to use those celestial bodies to find position at sea. And then eventually I'll show you how once you get a line of position on the chart, what do you do with all that? How do you mix it with your dead reckoning? And how do you do a running fix? And how do you practically navigate using this stuff? How does it work on a map? To find your position at sea, to keep safe, and to keep going. So if that interests you, if you're into that kind of thing, keep posted and see me back next time. Again, I'm George Trimble. I'm grateful for your visiting with me here today, and goodbye.